Okay, folks, welcome to the third lecture. It's the second lecture on linear functions, and in this lecture, we're going to examine the first general equation of linear functions, which is this guy here. Y is equal to mx plus c. We'll be looking at when do you use this equation and then some practical applications of it. So first of all, linear functions, they're denoted by this general equation. Now in science, we normally say y is equal to ax plus b. But in the leave and cert, they use y is equal to mx plus c, so this is the one I'm going to stay with. And there's two real bits from this equation. C is the y-intercept, it's b in this one, and m is the slope, and in that case it's a. So first thing guys is I hope you even looking at this slide you'll realize that these letters can change all the time. In statistics it's very often called bx plus a. So it's just important to realize there's one bit that has the x part, that's the slope, and the bit that doesn't have a variable, an x bit, that's the y-intercept. So we'll examine the y-intercept first. But really, we use this equation when you're looking at a graph of a function. This is the most effective way of determining the equation, is when we have the graph, this is the equation to use. So the y-intercept, it's simply where your curve or your line cuts the y-axis. So in this case, c is just equal to 3. In science, this is often the initial conditions, because usually we're often looking at time on the x-axis, and often what we're looking at here is the initial conditions of whatever system we're examining. Here's another plot, a graph, and here we can see that the y-intercept is -1. So that's the first part done. You simply just read it off the graph. What is the y-intercept? The slope, and I always do this, the slope, guys, is critical. In science, we often call slope the rate. So anytime you see the word rate, rate of change, rate of growth, rate of decay, in science, we're always talking about the slope. It's critical. It's what scientists do. They examine things as they change. How quickly are they changing? What's the rate of change? It's a huge part of what scientists do. Whatever you do, guys, take particular care with the slope and especially its sign. Just in general terms, the slope is the rise over the run. So in this example here, it'll be 100 meters over 300 meters, so the slope is 1/3. It rises 1 step or 1 mile for every 3 miles we drive. Usually on a graph, it's often called delta y. Delta, Greek letter, means change. The change in y. How much has the vertical value changed and how much has the horizontal part changed? Delta y over delta x is another way of saying the slope. So delta, guys, you get used to delta. Delta just means the change in a variable. Delta T, the change in temperature. This is critical. As you go from left to right, because obviously either of these slopes could be regarded as uphill or downhill, but it's as you go from left to right. If it's uphill, it's a positive slope. If it's downhill, it's a negative slope. Regardless of what your maths tells you, if you're looking at a graph and it's rising as you go from left to right, its slope must be positive. Do not make a mistake, guys, with these. If you make a mistake with the slope, especially at sine, you're going to lose most of the marks for that question. So be really, really careful. Just simply in terms of business, say if you were giving a business presentation and you went in and you told your bosses, oh, these are my sales over the last few months, and then you realize, oh, I'd actually made a little mistake, whereas the slope should be minus. It tells a completely different story. So just, it's not a small mistake, guys. To get the slope wrong, to get its sign wrong, is a huge error. You really could not be more incorrect. So we'll take a look at a few examples. And really what I'm trying to teach you here, guys, is how to do this without getting out a calculator or anything like that. It's a visual exercise. So once you're given your curve, I'll call them curves, guys. A straight line technically is still a curve. And there's loads of different points of interest. What we're looking for a point of interest, guys, is one that passes through an obvious kind of intersection of two values. Not something sitting in the middle here like this. This is not a good point because you're now trying to read decimals and stuff like that. So there's several points we could use to get the slope. And once you pick 2 points, draw a horizontal line to represent them. So really you want to join your 2 points of interest like this. And now the vertical change is 3. We're looking for just the distance between 7 and 4. This value should always be positive. It's merely a distance. There's our horizontal change, which is also 3. Because the slope is uphill, it must be positive. So there's our slope, 3 over 3, which is plus 1. Again, very important, guys, that it's a positive slope. But obviously, just the 1 written on its own implies that it's positive. So, you know the story. Pause the video and have a go at this question. What's the slope of this line? So again, guys, pick a few points. So you could draw a triangle between any 2 of those points, determine the rise, what's the vertical change, determine the horizontal change, and write one over the other. Remember to get the sign of the slope correct. Here's another one. Again, pause the video. What's the slope of this line? Okay, so we'll push on. So you must practice these, guys, because you'll need this skill for when we move on to the next stage, when we determine the equation. So now we're going to look at determining the whole equation using this formula. Again, remember, very commonly written ax plus b. The bit that's on its own, guys, is the y-intercept. The bit in front of x is the slope. So don't think that the first value is the slope and the second value is the y-intercept. It's not like that, because we could write an equation y is equal to 4 minus 3x. That's your y-intercept and that's your slope. So just be really clear, whatever sits with the variable is your slope, and whatever sits on its own is the y-intercept. This is just reviewing what we were saying. X and Y are our input and output. A and B are just values. They're fixed for a straight line. And that's what we're usually trying to determine. What is A, what is B? But we're going to keep using Y is equal to mx plus c, which of course is the last to appear. So use this equation when you're given a straight line graph, as I said. So when you have the graph in front of you, or in a more practical application when you have a scenario with a fixed part and a rate part. We'll see these towards the end of the lecture. We're going to take a look at just determining the equation of a straight line graph first. So here we're given a graph, guys. 3 things we're looking for. What's the y-intercept? The y-intercept, I hope you'll agree, is plus 2. What's the direction of what's the sign on the slope? Is it positive or negative? It's uphill as we go from left to right, so the slope is positive. And finally, you need to pick 2 points. I picked this point and this point here. Draw a vertical line to join them, draw a horizontal line. The distance between here, so we're just looking for the distance, guys. Don't worry about signs, minuses. The distance is 8. The distance here is 1. So my slope is 8 over 1. Now I have the values. Y is equal to 8x plus 2. So you notice I haven't used the y2 minus y1, x2 minus x1. It's a visual exercise, guys. Once you get used to these, you should be able to determine the equation of a line literally within 20-30 seconds. Here's another one. Y-intercept is plus 5. The slope is negative. I'm going to pick this point and this point. Just looking for any other valid points. Up here is another one. Now the vertical change, guys, don't be worried with 5 and minus 2. The distance of that vertical bit is 7. The distance here is 2. So my slope is, be careful, it's not 7 over 2, it's minus 7 over 2. And now I have the components of my equation. Y is equal to minus 7 over 2x plus 5. Now when we're talking about equation, guys, generally in maths they don't like a rational term, a fraction. So we multiply every term by 2 to get rid of that fraction. And finally then, guys, again in maths, if possible, try not to start with a negative term. So there's the correct equation there. So notice now, there's the y-intercept. Well, no, it's not actually the y-intercept. We have to divide everything by 2. But what I'm trying to say is, don't always expect equations to be written in this slope first, y-intercept second kind of scenario. So that's the equation of that graph there. So pause the video and determine the equation, determine the function shown below. Now be careful, you're going to have to use M and C, so just be careful. They're your axes. So this is really your X and this is really your Y. But it's the same process. What's the function shown here? Here's another one. And again, T is going to replace your X value and Q is going to replace your Y value. So your equation, guys, should be written as Q is equal to something T plus something else. Not X and Y, because you will lose marks. If you don't use the correct variables, you're not going to get the marks. This was an example we looked at in lecture 2, I think, maybe lecture 1. We were given this data, so a scientist has recorded this data. We write the data as coordinates. Remember, the input value always goes first. That's your input. Input, guys, always appears on the top of these tables. If the table is written correctly, the input should always be on top and the output on the bottom. So that kind of helps you as well. And from this, guys, we marked off our coordinates on a graph. Now we draw a best fit line. Notice how the line doesn't pass through every point. This is normal in science, guys. This is what you will typically get. From here, y-intercept is 0.2. And then we have to pick 2 points, guys, that are on the line. So I'm picking these 2 values because they do kind of, our best fit line passes through them. And there's our vertical change. The vertical change over the horizontal change. So our slope is 0.1. We can tell it's a positive slope. So here's now using y is equal to mx plus c. M is 0.2. M is 0.1. C is 0.2. But our x value is time, t. Our y value is length. and that's where our function comes from. So it's essential, guys, to be able to use the correct variables. Don't write y is equal to 0.1x plus 0.2, because x and y are not the variables in this case. Here's one for you guys to try. Okay, so we'll just get the button up. Now, in this case, guys, I've grayed out part A because I've actually done that for you. I don't want you to be breaking your hearts writing these, drawing out the graph. But from the graph, which is on the next slide, determine the slope and equation of your best fit line. So here's the data. Here's our best fit line. And just to make your lives a little bit easier, there's 2 points off of that best fit line. Notice there are none of the original points here. So the 2 points I've picked are actually not off of here. Because once you've drawn your best fit line, guys, you ignore that table. And now there's your 2 points. You can draw a vertical line, work out the vertical distance, delta y, work out the horizontal distance, delta x. Is it a positive or negative slope? And then work out c. Remember to use the right variables when you're writing your equation. So your equation should be n is equal to something t plus something else. Don't write x and y. Now, things can get a bit complex in science. We're looking at the photoelectric effect, and we've done an experiment, and here's our experimental results with a best fit line. Determine the slope of this line. Well, the vertical change is this. Now notice that's 9.2, but it's 9.2 by 10 to the power of minus 19. This is 2.6 by 10 to the power of minus 19. On the bottom, guys, the horizontal distance is just 1, but it's 1 by 10 to the power of 15. So when we work this out, remember, because these values are the same, we just simply subtract 9.2 minus 6.6. 2.6 gives us 6.6. 2 minus 1 gives us 1. Numbers do what numbers do, 6.6, and powers do what powers do. Minus 19 minus 15 is minus 34. So that's our slope. And I know it looks odd, but that's science, guys. You're going to come across some very strange values as you progress through your careers. As long as you understand the rules that govern everything, you'll be okay. So now we have the slope, guys. We're just going to go to the next slide. Joule seconds. And now we want to determine the equation. So we've kind of extrapolated, even though our data only brought us down to here, we get a ruler and we continue the line until we find where it cuts the y-axis. We're looking for C. Where does the line cut the vertical axis? Often, guys, you have to extrapolate your data. That means extend the line beyond the domain and range of your original experiment. So we've worked out the slope. C, where's the y-intercept? It's at minus 4, but minus 4 by 10 to the minus 19. And now E is equal to HF minus theta. E, so H is the slope, guys, and theta is the initial condition. Sorry, that's phi actually, not theta. So there's your function written out in full. So it's just to try and show you guys that even when you're dealing with kind of more complex looking graphs, the technique is still the same. So remember, y is equal to mx plus c. When you have the graph, that's the best equation to use. Now we're going to look at some other applications, so kind of practical scenarios. And often a scenario, it's hard to describe. Once you see the next slides, you'll understand what I'm saying. Often a scenario has a fixed part and then a variable part. We can use this equation again to determine the function that's been described. How do we find C? Well, the fixed part of the scenario is usually the initial conditions when t is equal to 0, like I said earlier. This is your y-intercept, in other words, it's C. How do we find M? The variable bit is usually in the form of a rate. So if the question says something about miles per hour or for every kilometer or by the slash symbol, you can be pretty sure you're dealing with a rate, and a rate, guys, is your slope. So we'll take a look at an example most of you will be familiar with, a taxi. Taxi has a pickup fare of 210 and then charges 0.85 per kilometer travelled. Write a linear expression to describe the relationship between distance driven and taxi fare. How much will a 12-kilometer journey cost? So we need to use this function then to answer part B and C. So in a taxi, guys, when you get into a taxi, that's the fixed charge, your pickup fare. So say if you called out a taxi and then you decided you didn't want to go anywhere, you should still be paying the taxi his pickup fare, even though 0 kilometers were driven. So we'll take a look. So the pickup fee, that's the fixed part, like I said. So C is equal to €2.10. The cost per mile is the rate. So that should be cost per kilometer. Is 0.85. And the general function describing the taxi fare is, remember, y is equal to mx plus c. Y is equal, so there's my slope, there's my fixed bit, and finally though, guys, x is the kilometers driven. So we're going to replace x with kilometers, km, and we're going to replace y with the fare. So kilometers is our input, so how far you drive that's your choice. You control how far you drive because you choose it. And then the output is the fare. So this is part A now. This is the function that describes that taxi fare system. Now that we've established this, guys, we can answer parts B and C. How much will a 12-kilometer journey cost? At km is equal to 12, we just feed it into the formula. And a 12-kilometer journey is going to cost €12.30. If a passenger pays €18.25, how far did she travel? Now this is trickier, guys, because we know F, but we don't know km. So we have to manipulate the function. We need to get km on its own. So here's our function. First step, we want to get km on its own. Just two bits affecting it, this bit and this bit. We always move the furthest away bit first. So this is going to be removed first. Subtract €2.10 from both sides. And then, guys, we want to get rid of the 0 because we want km on its own. We want to get rid of that 0.85. It's joined on by multiplication. So we divide both sides by 0.85. Just to be neat, I've written out my kilometers on the left to be correct. Don't need to do that for this case because we're working through to a solution, but I just want to show you the right way to do things all the time. And now we just simply feed the fare in for here. And we get our answer out then. That passenger travelled 19 kilometres to incur a fare of €18.25. So now, again, very similar scenario, guys. I'll just put it all up. So it's pretty much the exact same process as the taxi example. So please give that one a go. Again, in the tests, I'll be asking you either A, B, or C, or maybe all three, depending on how the randomization works for you. And now this one's a bit trickier, guys. So this one's going to make you scratch your heads a little bit more. But it's the same scenario, but just different, a little bit more complex. So a new van has been tested. So a model van. This is actually a Volkswagen T6. So new van has been tested. At the start of the test, the fuel tank is full to its 80 litres capacity. After several hours of testing, it was determined that the van consumes 1 litre of fuel for every 12 kilometres driven. Develop a function which relates the fuel left in the tank, F, and kilometres driven. After a journey, 35 litres are left in the tank, so determine the number of miles driven on that particular journey. So it's a little bit tricky, guys. I'm not going to say any more. Just do your best. And you will find that this semester, guys, I am going to be thrown, like it is college, like you are going to be given problems that sometimes you will be scratching your head. If it's wrecking your head too much, just drop me a line and we can take a look at them in the tutorial. Okay, folks, I think that finishes us up for this lecture. So thanks again for watching, and we shall meet again for lecture 4.